So let me join everybody else and thank the organizers for putting together this very nice conference. So what I'm going to talk about is some work we are trying to do, sort of trying to exploit these coupling of light and matter for quantum information processing. So just to set the stage here, of course we all know which kind of system we are talking about. We have this atom here. Why is this so bad? I don't know. Never mind. If this light field is strongly confined around a waveguide, then what can happen is, of course, is that our atom preferentially decays into this waveguide here, or it can decay to the side. So for specifying this model, there's really one number which matters, and that is this beta factor. Once I know the beta factor, I have a mathematical model, and I'm a theorist, so I can just sit down and solve it and get out nice stuff. Sort of, as Jeff Kimball pointed out, earlier today, there's sort of an equivalent setup, which you can think of is an atom in a cavity. If this cavity here is broad, then what happens is, as Jeff said, that this cavity mediates effectively an interaction into this forward direction. And if we take the limit where the cavity is broad and we keep a fixed cooperativity, then in this limit here, this here has a good rate of emitting in the forward direction, which is 4g squared over kappa gamma. And then what happens is that this model here is essentially equivalent to the model up here. And so whether we're going to talk about C, the cooperativity, or beta, it is sort of the same. There are subtle differences, but much of the intuition gained from one can be used in the other one. So what we want to do is we want to use this system to do quantum information processing. Now, this was one of the oldest proposals, actually already back in 1995. Chirac and Soller suggested that this here could be a method of making actually gates between atoms. So the idea is that one atom emits a photon, bounces back and forth between these mirrors, and is finally absorbed in the other one. Now, this works in principle, and there has been literally thousands of theory papers investigating this, and not a single experiment have actually done this thing where one atom emits one and is absorbed in the other one, not in the optical regime. And the problem is that it doesn't work very well. If you sit down and do the math of this, what you get out is that the fidelity is very, very limited. So the error, so the way I express this is in terms of the scaling, so the error goes as 1 over the square root of the cooperativity. And for current experiment, the cooperativity is just limited, maybe 10, maybe 100, and then maybe there's a factor of 3 above, and then what you get out of this formula here is just very, very bad. So at first sight, it doesn't look very, very promising. And indeed, for the waveguide, you can sit down and do the same thing. Now there are not thousands of theory articles, I know one, that's my own. And what we sat down and did was we investigated, there's a reference you cannot see, it's down here below. We sat down, investigated, and an analogy with this, when we sat down and figured out what is the fidelity of this, then again we got the square root of scaling here, and even if you get 99, what you get from this is not very promising. So fortunately, there's hope. Okay, so for the past 15 years, I've sort of on and off been working on, can we actually find some solution to this? And actually there are some solutions where we can overcome the scaling here and get something better. And so here's a list of possibilities which randomly coincides with the one I've been working on. So there are those ideas, but these are just the one that I remember because it's myself who have worked on it. So what I'm going to do today in this talk is I want to talk about some of the ones where we've had some recent nice results, where we sort of try to overcome this bad scaling that you can get. All right, so the first one is some work we're doing on, we're trying to use this coupling to waveguide to entangle superconducting qubits with light. And the idea is we want to use molecules in waveguide. And so the idea is something we already heard about. It's also, there's a nice reference down here. To a paper by Chirac and Soller all the way back in 1995, where they talk about how can we actually make probabilistic entanglement, right? And what they did was that they had two atoms in the lambda configuration, and either one or the other one could emit a photon, and then this photon here was sort of sent on a beam splitter. You don't know where you got it from, so when you have a click, what happens is that you end up in an entangled state of these two qubits. So this is a nice protocol. It works. You know, you don't need waveguides, as was mentioned yesterday. Also, you can do this no matter what the collection efficiency is. It's just very, very tedious to actually do it in the lab. So what you want to do is you want to put, you know, so you have this here, exactly a nice process that, for instance, Chris Monroe has been doing something where he entangles different ion traps in this way, and it's actually very nice and highly important if you want to do quantum communication over long distances. And what you want to do is you want to put it into a waveguide because that increases the efficiency, but that's about it. So what I want to talk about here is something where I think the waveguide will really make a substantial difference. And this is actually what we want to do is we would like to connect light to superconducting qubits. Now, this is just, you know, a picture from the Skjold group. We heard about this yesterday where, you know, superconducting people are doing miracles, right? Their system just works, it's fantastic, so they're building a quantum computer. Now, there's one thing that they cannot do, at least at the moment, is that, as Louis Roscoe also discussed, they're not very good at connecting their superconducting systems to light. So there are many ideas on how one could do it, many proposals from theorists, including myself, and typically what one says is, okay, let's take a real atom and put it there, and you know, then there's some kind of interaction, and this atom talks to the superconductor, and it talks to the light, so this is the way we want to do it. So all we want to do is we want to have some entanglement scheme along the same you know, ideas of what we did there. So what we take is that we take a laser light and we shine it onto this qubit, onto this atom here. And as Louis Roscoe discussed, now the superconducting people sitting here in the front gets upset. Okay, don't bring your light anywhere near my qubits because one photon actually has the energy corresponding to the binding energy of a hell of a lot of Cooper pairs. So if one photon is absorbed, and you know you're looking at the tunneling of one, and one photon comes in and breaks 1,000 Cooper pairs, you're kind of dead. Okay, so these systems here are very, very sensitive to light. So what we want to do is, if we want to do something like this, we should make sure we send in as little light as possible. So what we want to do is we want to put this atom here in a waveguide. And so the goal we sort of set out to do was, can we sort of do this entanglement between the superconducting qubit and light, sending in the absolute minimum amount of light that we sort of can do? Well, what's the minimal amount of light we can send in? That's one photon. So we want to see, can we do this by sending in one photon? Yes, in principle we can, right? Because if this atom here is strongly coupled to the waveguide, send in one photon, then in principle, you know, we can have this reflection. Okay, so what inspires us to do this was a discussion with Stanley Fayez, who did some very nice experiment in the group of Sandukdar. So what they did was they took some organic molecules and put it into a hollow core optical fiber and cooled them down, and actually what they found was they can have a reasonably good coupling. Not very nice, you know, no 99, but they get 10%, which is a good start. And nice things about these molecules here is that at low temperatures they can actually have very nice lines. They can be radiatively limited, nearly. Bad thing is it's essentially a two-level system. Okay, good thing is it's a good two-level system. Bad thing, it's a two-level system. Because a two-level system is not a very good qubit. You can excite and then you decay, and you can excite and you decay, and you can do nothing else. So what we want to do is we want to use these molecules here to mediate the interaction. All right, so how do you want to do it? Well, if you pick these organic molecules right, and you know you can just have some chemistry, you know, mixing with various liquids, and out comes the molecule. If you do it right, you can have molecules which have strong AC Stark shift, right? Just because the excited state of some organic molecule, has a dipole moment. So what we want to do is suppose that we have a charged qubit where, the qubit is that either the Cooper pair is down here or down here. What will happen is that this will couple to the transition frequency of this molecule here. So suppose that now my Cooper pair is down here. Then what will happen is that my transition frequency will be at this point. If I move my Cooper pair up to the other end, my transition frequency will change. Simply because there is a dipole moment in the excited state. If I move the Cooper pair back, it shifts down again. So if you sit down and do the numbers, say that this differential AC Stark shift corresponds to a dBi, you're 500 nanometer away, then the shift can be from just a single Cooper pair jumping, can be something on the order of 45 megahertz, which is actually larger than the line width of these, which is like on the typical 20 megahertz line width. So it really is that this line here, by one Cooper pair shifting, you can actually switch the line completely. So in principle, it sort of gives a strong coupling. So if I send in a photon at this frequency here, what will happen is that, well, if the Cooper pair is down here, this photon here doesn't see the molecular line, so it just goes through. On the other hand, if my Cooper pair is up here, what will happen is that light will be reflected. So in principle, this here is sufficient to do this job that I set out to do of entangling my light with my superconductor by sending in a single photon. All right, except that this here would never ever work, okay? Because the qubit, the way I've described it, is a so-called charge qubit. And I think that the worst possible qubit that anybody has ever been made in terms of coherence times are charge qubits. They just die extremely rapidly. And so the problem is that, you know, my qubit coupled to my molecule and coupled to any other dipole moment around, and this just shifts this thing here around. So in fact, the superconductors, they wouldn't call this coupling to the molecule a nice coherent coupling. They would call it charge noise. And this is what completely killed, you know, superconducting qubits in the beginning. So what these superconducting people have spent 10 years on is trying as hard as possible to get rid of this coupling to this one here, and they have actually become really good at it. So for real qubits, this coupling here is dead. All right. So in particular, you know, what they do in the superconducting qubits is that the first thing is you go to charge degeneracy, where, you know, your eigenstates are not sitting here or there, but rather this superposition where you're basically tunneling back and forth. Right. So this means that essentially this coupling to this molecule here would be completely averaged out. So if you are to make some of this work, well, what we had was we came up with a different idea, actually again inspired by an experiment by Vahid Sandokdar, cited down here, sorry about that, is that, well, let's not take one molecule, let's take two molecules. If we, and this was actually observed experimentally in this reference here, so you can't see it, so I can claim whatever, but what they did was that they looked around and then they found molecules, and then they found two molecules which were very, very close. So if these molecules were very, very close, it meant that there was an optical dipole-dipole interaction between them. So essentially the excitations were flipping back and forth between these two molecules. So what could happen is that if you tune this into resonance, then actually this interaction won't average out. So essentially what is happening is that these here sort of swing in, you know, in resonance with these. And this means that there is, in fact, still a resonant interaction which doesn't average out between this molecule and this Cooper pair. So what we sat down and did in a little theory is, if you start with the molecule in your ground state and you send in a blue photon here on sort of the upper of the two dress state of these two molecules here, what will happen is that you go up, then you can sort of exchange an excitation with your qubit and you go down again. Right? And then you emit essentially a red photon. So now what essentially you can do is you can make one of these Raman transitions where, you know, it's not the ground state of the atom, but it is the ground state of the qubit acting as the sort of the degenerate ground state. All right? So the way you will then use this to entangle two qubits is you make two of these, and, you know, make an interferometer, send in blue light, and then one of these emits a red one, and then you know, a photon comes out, and you have a click on these two detectors. You don't know which one, and you are entangled. And you say, yeah. So what we're doing, we are currently going through the numbers once more, but what we sort of get at the moment is if we have this coupling here of beta of 10%, and we go into this strong coupling regime, maybe you didn't want to do it with one photon, but maybe with 10 photons or something like that. So you can actually go into a regime where you can do this thing that I set out, entangle light with superconductors by really sending in only one photon, almost. All right. So let me now switch gear a little bit and talk about a different project where we are again trying to exploit this bad coupling of light to atoms to see can we actually still do something nice in terms of having something, with a good fidelity. And this is, now we're trying again, this is, this thing over here actually works kind of nicely, right? So it happens with a low probability. Most of the time it fails, but once in a while you get a click, and then once you have a click, you have something nice. Okay, so this is what people usually talk about when they do entanglement generation. There we are sort of happy, okay, it worked, and now we proceed, and so on. On the other hand, over here, when we are talking about gates, no, people, what they always write down is, okay, now I want this to happen. I want, for instance, this phase evolution to happen. This is what should happen. We talk about, we want it deterministic, we have, a very good fidelity, and so on. The problem is that this is what everybody has been trying to do, and when you do this, we get this bad scaling of the fidelity. So what we set out to ask ourselves the question, well, can we get some of the same advantages over here? So what if we just briefly give up a little bit on this fact that it has to be deterministic? Okay, so can we make a gate where somebody comes and say, okay, now it works. And then when it worked, it's not an entangle state being generated, but it is instead this gate operation here being made. So this is sort of a different, I don't know, I shouldn't call it paradigm, but a different concept. Can we make it such that, somebody says, okay, now it worked, now you had actually a gate, and you can use this to process information instead of just generating an entangle state here. All right, so the way we set about to do this is we were inspired by some work by Lu-Ming Duang and Jeff Kimball, cited down here again, once again. Not the one we have heard about all the time, but a follow-up paper where they actually asked, okay, can we make a gate between two atoms in a cavity? And what they said is, okay, let's say that we have this level structure over here, and we scatter a photon. Now, if there's any atom in 0, then we've heard about 0 times, then this cavity here is completely blocked, the photon comes in. There, this was wrong.
Good, good.
Yeah.
Good animation.
Okay, so what comes in, so if there's an atom in 0, it will interact. But if both atoms are on 1, this is what I was supposed to say, if both atoms are on 1, then what happens is that the photon comes in, bounces back and forth, and it will eventually leave. Whereas, if any of the atoms are on 0, it will come in, it will scatter off the face of this cavity here and go out. And if you sit down and do the math, there's a pi phase shift between these two things. And so this here actually realizes exactly a phase gate. Okay, this works in principle, provided that you have no losses. But, Lu-Ming and Jeff had a proposal for how to fix this. You put a cavity detector here, and, you detect, did the photon go out? The detector goes click, and then you are pretty sure that it actually worked pretty well. So a very nice idea, and this is what we're going to copy. Just make a slight change of it. And the problem is that the way it's described here is to make this work really efficiently. Well, first of all, you should have a single photon source. They're expensive. You should have a good photodetector. They're also hard to get, and you should make sure that you don't have any light being lost. So what we want to do is, well, one way to make both a photon detector and a photon source is actually to put an atom in a cavity. So we could put a separate cavity, but we could also, add one more atoms to the same cavity. So what can now happen is that, suppose that this atom has a level structure like this, then essentially this atom here, this extra atom here, I can drive it over here, it emits a photon, bounces back and forth, and is then reabsorbed over here. Okay, go through the math, this works exactly like the same as having the photon source outside, and so it makes a gate. Now, the nice thing is, if we assume that this transition over here is closed, what will happen if the photon is lost is, well, I go over here, the photon, drifts somewhere else, and my atom is left down here. So if In the end, I ask, which state is this atom in? Well, if it's an F, I know my photon was lost. But if it's in G, it's like I have detected the photon again. It went in there, scattered, and went back out. So if this transition is closed, what I can really have is that I can have a heralding operation. If this atom here says, okay, I'm in G, I think it worked, then you can have a very nice fidelity in this case. All right? The only problem is that nature doesn't have any atom looking like this. If I want to say that I can drive this transition, then I can also decay back. So this atom does not exist, but we make it. All you need to do is to make a 2-photon transition. So you go up with an optical field to a different excited state, take a microwave field, drive over here. Then effectively, if this detuning is big enough, then it is as if you have a closed transition, if this one here is closed. Do the math. The further you detune, the smaller you can make the error. And very nice, this is just from some numerical simulation, and this here is a theory, is analytical curve. Is, look at the error we get. This is a fidelity 1 minus 10 to the minus 6 with a cooperativity of 10. Okay, so we can really actually show we can make this error arbitrarily small. Of course, the cavity still matters. Okay, the way the cavity enters is through the probability. Right. So there's a probability, and there's the worse the cavity is, the more likely is it that we fail. So the failure probability now goes as 1 over the square root of the cooperativity. So what has happened is that what was used to be infidelity is now converted into into probability of failing. All right, do some realistic numbers for rubidium due to the level structure and so on. We think that one can get like realistically a fidelity of 1 minus 10 to the minus 3. Alright, so now we can ask ourselves, where could such a gate be useful? Because it's different than in the usual quantum computer where you really want things to succeed. So the natural place to apply this would be, for instance, in something like a quantum repeater, because we know something like DLCC protocols, we know that they actually work even with probabilistic entanglement swapping. So we just try to apply this thing and see how well does such a quantum repeater actually works. So the idea in this quantum repeater is that one creates entanglement over short distances, and then one have these entangled using the protocol I discussed in the beginning. Then we use this atom here to make a gate between these, and thereby the entanglement gets swapped to larger distances. So now we just sat down and simulated a quantum repeater and see how well it performs. And the nice thing is we know that this still works even with probabilistic gates. So now it's just looking at how good rate do we get. And so we try to do an extremely good job at sort of optimizing all the existing protocols in the nature, in the literature. What can you do this, or you can do that, you can do that, and we try to optimize everything and really do the right thing. And so this is what we find in terms of rate, where we take this heralded gate, which the nice thing is that it works really nicely. And then we compare it to, let's say that we have a deterministic gate with a fidelity which goes as 1 over c. So actually, if you compare, if you throw away the averaging, this gate over here works much, much better, right? Because it goes as 1 over c, whereas this has a failure rate of 1 over square root of c. But when we actually try to apply it in a protocol, it is much, much more important that you actually, once you do stuff, you do it right. All right? So this is not only here. This, of course, it applies in life in general. It is much nicer that people just give up and say ask for help instead of screwing things up and doing something wrong. Okay? So this also applies here. In this protocol, it's nicer that we actually once in a while give up and say now we failed. But then as long as once we do something good, it should be good. All right. So let me now switch how I'm doing on time. Okay. 15 minutes. I'm talking way too fast. All right, so let me go through this in much detail. All right, so this is the final example of what I want to say today, and an example of where we can, do something to get around this 1 over c scaling. And so the idea is that now we want to turn the game around a little bit, and before we use this scattering gate to do gates on atom, now we want to do it again to make gates between photons. So there's a reference down here to Jeff and Lu Ming's first paper on this. Damn. All right, so again, the idea is if we have this one-sided cavity here, instead of making a gate on the atom, we can also do it to make gates on photon. So again, if my atom is in state 0, my photon won't be able to go in there. If my atom is in state 1, it will actually go in there, bounce around a few times, and go out. And so, yeah. So if I can actually do what Misha is showing, and Jeff Thompson showed in the experiment, I can do this thing where I first send in a single photon, flip the atom, then this would be a way to make gates between photons. Right. Now the problem is that this thing here, of course, requires very good cavities and having atoms strongly coupled. So what we want to do, what we want to do is we want to do what Thomas Pohl talked about in the first talk of this session, is we want to use the Rydberg blockade to do this. Okay, so the first thing, the way the protocol that we came up with work, is that first we try to store a photon in this ensemble here. This is a well-studied process. It worked very well. It has an efficiency of going in there, which is 1 over the number of atoms times the cooperativity. So if you just put enough atoms in there, it sort of works in principle. And people have been doing this very well. Okay, so we do this sort of EIT storage. And then what happens is, we have a level structure similar to one that Thomas Pohl talked about that we store in this Rydberg level. Yes, and we can make this process here very, very efficient if we want to. Then we transfer this to a new state just to have it locked so that the atom, if it's stored, it actually stays in this state. And the nice thing again is that because we store it in a Rydberg state, then it actually strongly interacts with all the other nearby atoms if they are also in a Rydberg state. This is the big Rydberg blockade. So essentially this one here shift all the other atoms out of resonance. So if I now try to send in another photon, then I cannot have this EIT. So what will happen is that they will instead not go into the cavity, but because now the cavity is blocked, I won't have the process that Thomas talked about where you go in and you are lost here. What will actually happen is that you go in, hit the face of the cavity, and it's reflected back. Right? Because there is this whole cloud of atoms which are blocked by this single one excitation. All right. So now the important point is that before, everything I did before, it was always the cooperativity of the single atom which matters. Now what begins to matter is what's the cooperativity of all the atoms being blocked. Because all of those atoms being blocked, well, they are now essentially two-level system. And so then they are two-level system talking with the cavity, and you solve the scattering dynamics from a photon from a cavity with two-level system. All the other atoms are under EIT, so they are just transparent. So the only atoms which basically matters are those which are blocked. So the figure of merit is no longer the single atom cooperativity, but this cooperativity times the number of blocked atoms. And if this is much larger than 1, I'm basically in a regime where I can do what I want. All right. Yeah, more of these stupid animation. All right, so this is essentially a phase gate on the photon, because if I stored my first photon, if it was, let me go back. No, I shouldn't have done that. If I store my first photon, then I have an excitation here, and I cannot send in a second one. If I had no photon in the first pulse, then the second photon was not blocked and could go in there. So this essentially makes a phase gate between the photon, depending on, in the sort of photon number representation, if the qubit is whether there's 0 or 1 photon. Now, I don't know exactly how these results relate to the discussion you had before, after Thomas Pohl's law, but when we do this math, right, what we do get is that if we take, just this single rail encoding where the qubit is 0 or 1 photon, we get a fidelity which is 1 over C times NB. Now you can also do it in a different regime where you sort of say, okay, let's do the same as I did before and say, let's do this conditional interaction where, you know, instead of saying that my photon is 0 or 1 photon here, I say that my photon is either here or here. This is sort of a dual rail encoding, and I have my second photon, which is 1 photon here or here. And then, you know, beam splitters and playing around, I can have exactly the same dynamics. I can make a gate between this dual rail encoding. And the nice thing about the dual rail encoding is that now I can actually really see if something was lost because I send in 2 photons, I should get 2 photons out. If I don't, I know that something was wrong. So if I now condition on getting 2 photons out, I can get a fidelity, conditional fidelity, which is 1 over c n b squared. All right? And just for comparison to, you know, the free space, what we gain with the cavity is that our parameter, which is c times nb, is essentially the finesse of the optical cavity times the Bloch cooperativity. So if you are worried about your Bloch cooperativity being too small, put it in a cavity and you can increase it by the finesse to make it work better. Yes?
And the probability of getting both clicks, is that
goes like this. Yes. Right. Yes. And just to figure out, you know, how well does this actually work, we did the same thing and sent it through a repeater and just compared what is the rate. So what we compare here is, you know, standard ensemble-based repeaters. There are millions of proposals on, you know, how to do that, so we tried to pick the best one. And then we compared, depending a little bit on what are your assumption about what you can do locally, you get 3 different curves. And then what we compare is how well do our gate actually works. And sort of there is sort of a threshold around 7 or 8. If we have a C and B around 7 or 8, then actually in terms of repeater performance, this gate here is better than doing the linear optics. Below that, the fidelity is too low and you shouldn't do this. All right. Yes. So let me go to the conclusion. Probably too early. All right, so what I've tried to argue here is that, you know, we need this coupling of light and matter. We need it for, you know, doing quantum communication. If we try to do it directly, if we're not careful, then we typically get something bad. But, you know, there's hope. So if you play around with these parameters, you can get a better scaling, depending a little bit on the protocol, and there's always some price you have to pay. But, you know, that's just what you'll have to do. So I've given you 3 examples here. So one of them is this approach that we're trying to do to see if we can couple, you know, light and superconductors at very low light levels, meaning 1 photons where we don't burn these superconductors. The other thing we try to do is, you know, if we are willing to give up on this requirement that the gate should happen, you know, deterministically, but we are willing to accept a small failure probability, then we can actually make something which works with a fidelity which we can make arbitrarily close to 1. You know, the closer we want to do, there's a price to pay in terms of time, but that's it. All right. And then finally, you know, there's this other thing that we can do, and we can try to, you know, use the Rydberg blockade, combine it with optical cavity. Then we can actually get around this requirement of having to have efficient single atom coupling. All right. Let me just thank some people. So the main heroes are here. Sumanta Das works both on the, you know, Rydberg stuff and on the superconducting stuff. For the superconducting stuff, we had a lot of collaboration with a group in Paris of Etienne Perron and Philippe Granger, where in particular André Granger did a lot of work. Johannes Bohr did all the work on the heralded gate. Johannes is now here working at Harvard, so he's sitting in the audience down here. He also did all of the repeater work, which was a collaboration with Harvard, and we had a nice collaboration with Stanley Fayez from the University of Leiden for our work on superconductors. Thank you.
On the cavity, the second thing, the heralded gates, you went through it and you got this usual kind of 1 over square root c for the infidelity, and then you added, let's get rid of the decay path back. by a
Yes.
microwave, and then there was a miracle that said arbitrarily close to 0 for 1 minute step.
Yes.
Could you explain the miracle?
Well, the miracle is called Johannes, and he's saying back. So it's actually what we do is we sacrifice a little bit on the probability. So there are two things. So what works very nicely is that we just look at the phase of this reflected photon. Then you can set it up so that the phase is always pi. But what you need to do is you need to be very careful about going around setting this detuning here, right?
So you optimize that.
We-
It's all as a decay path, right? If you can go up even.
This decay way back here, what we show is that if you detune far enough, then this decay path here goes away. It's like doing a Raman transition, right? So then the decay is always over here on this path. Right, so if this here is far detuned and this one here is actually drawn badly, this one here should be near resonance, then essentially where you have the decay is over here and not here because this is far detuned. And the further you detune, this is what we have here, this is the detuning. The further you detune, you don't go back here. It's like a Raman transition. If you have a Raman transition, if you detune from here, you don't decay.
Conceptually, just simply, if you have a, like, imagine if you have one transition which is kind of nearly far bigger, right? It's not, it can, so then you just drive it back, the classical drive.
Yeah. So the further we detune, so lambda system, it goes away. We don't scatter here. We still have the same amount of decay, it just happens over here. Sorry.
So, if I refer back to your introduction, so all these things that you showed for the entanglement are basically comparative on the tennis condition between the two atoms, like one atom is comparative condition to the other, or whatever, all this Ferrari stuff, or whatever. So, and then you show that anywhere you, however you do it, then you get a scaling which one of those root of C.
Yes.
Now, if you have if you use dispersive coupling or this flip-flop coupling instead of then get something, then I mean I don't see immediately how it scales like this, but I'm asking you whether somehow it happens that it does scale like this eventually. This time, what I'm asking.
What happens is that it always scales like that. So okay, that's a bad answer. Okay, another bad answer is that there are 1,000 theory protocols, and I haven't looked through all of them. They always get the same. So whether a fundamental reason why it is square root, I don't have. Okay, this is just what all comes out. It is always there are two processes you're trying to minimize. And one is spontaneous emission and the other is cavity loss. And then you always you have to make a trade-off between these two, and you essentially have one big parameter, which is C, and then you need to divide that big parameter between these two processes. And then all the proposals that I have seen always end up with square root. Now, this is not saying that it's impossible to get better. I would like to have a proof that it's not better, but I don't. So, okay.
So you have the emission inside the cavity and the emission outside, and basically these are the two competing processes.
Yes.
So if it's dipole doesn't matter, it will be like the emission inside the cavity. That's what maybe.
Yeah, right. So now I think I get it. So now I'm talking about, now I really have this photon bouncing back and forth. And you could also have where you sort of go off resonant for the cavity. Now I got it. If you go off resonant for the cavity, you also have to, make a compromise with how far do you detune, and if you detune too far, you get too much spontaneous emission, so you have to do the same compromise, and once you do this compromise, you again end up with the same square root of C scaling. Now I got it.
So actually I was a little bit confused on this simple blockade repeater, scaling kind of looks worse than the single atom scaling. Or maybe I use like the rates. So what you plotted is rates, right?
Right. Okay. So if you really want to go into the detail, so okay. Stupid animation. So what is bad in this one? In these is bad in essentially all the ensemble-based repeaters, and that is that the initial stage where you sort of have to do the scattering, you have to do that at very low probability, and that just hurts you on the rate a lot compared to. No, right. So if you looked at the curves, I didn't explain it, so you probably didn't see it. There I had 3 sets of curves. And the best curve was where we assumed blockade. And once we assume blockade, then the numbers are good. Okay.
The standard's the same as single atom.
Johannes, you have it. It's sort of on the same order of magnitude.
Yes.
It's the same. Stupid animation. Maybe there's a faster solution. I mean, I can. Yeah, but now I gave up. And still I have to go through this. So the rates here, this is like 10 to the minus 1, but then this is, again, similar to what we did per repeater station. So I have to compare this to what most people are doing, I have to multiply it by the number of repeater stations. And then once I get up to that, I get like up to 1.5 per second at 1,000 kilometers, which is comparable to what we found for the single atom case.
Right. So